Okay, we are recording. I'm sharing my screen. Can everyone see the slides?
Yes, sir. It's
Okay,
visible.
sounds good. All right, guys. So, are there any questions from previous classes? Just let me know. We can go over it very quickly. But if not, let's move into convolutional neural networks. I call it the great leap into modern AI. Yeah. So, this was basically the start of all model AI architecture, and we are going to learn about what CNNs are and hopefully try and implement some of these ideas in the assignment that I think should revolve around CNNs, but I haven't decided it yet. But let's dive into it. Okay. So, what are the problems that we are interested to solve typically? Okay. Let's take this example. Let's take this image. Okay. Now, what do you want to understand from this image? Anybody, we can shout it out. What do we want to know when I give you this image?
What are the components of the image,
Yeah,
or
exactly.
what are the segments? What are the players?
Yeah, good.
Colors,
Yeah. Anything else?
time,
Description of the
maybe.
Description, context. Yes. Yeah. Very good. Yeah. So there are many things that we want to know from this image, and it's in fact, as we process this image via our brain is making a lot of these inferences about what's happening, right? We are typically interested in the image context, right? What is the context of this image? And we want to classify this image. So what is this an image of? Is it an image of an object or a human, or a living thing, non-living thing, all that, right? As someone pointed out, we are interested in image segmentation, right? We want to understand the components of the image. We want to understand what each of the components are. And often we are also interested in things like retrieval related tasks. That is, once you obtain information from this image, can you store it and then use it for some other purposes, right? So in terms of image context, this can be described as a man is walking his dogs on the road, right? This is some sort of a image context. And there are many features that you can add to this, right? A man is walking his dogs on a road in a park. Okay, very likely it looks like a park, but that all depends. And also you want to understand if you can segment out from this information about the human or the man or the dog and probably the trees around, right? So in essence, this problem of what has been tackled in computer vision for a long period of time, in around about the 1980s, they came up architectures to solve this particular problem, and what CNNs gave was this architectural backbone to solve this, right? To get from an image the context, classification, segmentation, and all that, right? But why an image in the first place, right? We want to understand that. Why an image? Why not any other sort of data? What is so special about an image, or maybe even other types of data? But an image is easy to contextualize. So what's so special about an image?
Captures relatively more information in a small space.
Um, but what is it about an image that does the data has some inherent structure in it? What do you think
There is no
about that
structure at
structure?
all. There is no data structure. I mean, data is no structure at all. You need
Sorry,
to extract.
come again. I didn't hear you.
I'm saying, unlike simple text,
Uh-huh.
image doesn't have structured data. So
Mhm.
maybe we need to extract the data
Mhm.
within the image, and that's where
So, but
uh,
what is something that's preserved in the image? Okay, and
The
that will tell
structure
you what
hierarchy of the
CNNs.
image is preserved, like
Mhm.
how the placement of the objects are in the
Yeah,
image.
yeah, yeah. So some form of a spatial correlation, right? Like you got to exploit the aspect that an image has some relationship where the nearby pixels, right? So if I take a small part of the image, the nearby pixels are in some way correlated with each other, right? So if I take this and this, there's some relationship spatially between these two areas of the image. So we need to somehow exploit this fact, and that's where this entire domain of convolutional neural networks came into existence, right? So let's talk about what are CNNs first, and then we can deep dive into them. So before I put it up, any idea what are CNNs? Because obviously we're going to talk about it, but I just want to know what sort of guesses you have about what they are. Anyway.
So where we basically have neural networks where one layer is being convoluted, and then the output is being.
But if you want to just say it in a simple sentence, what are they?
Mathematical operations.
Right. Okay, that's too simple. I'm just saying, make it a little bit more in between, right?
A deep
That
neural
is
network which
multiplication.
helps in building the hierarchy in images.
Oh, okay, very good. There are some points there. Hierarchy, that's very good. Then?
It's specific to images, like
Why? Why?
that I'm not sure.
Yeah, okay, cool. So I got some of the keywords there, but let me put it up on the screen so that we get these key points in, right? What are basically CNNs, often called convnets? They are a multi-layered hierarchical deep learning architecture. So this word hierarchical is very important. The idea being that there is a hierarchy in its organization. That means that the lowest level in information is getting built up to become more and more complex. Yes, if there's a question, just shout it out. And they have the ability to exploit spatial and temporal correlation in the data, right? This is very important. And images are such forms of data where there is spatial correlation, right? Just because we discussed things that are nearby in the image are highly correlated with each other. And this information and even temporal correlation, for some cases, time series data is also in some form has temporarily correlated data, right? Like if you have patterns that are changing across time in a specific way, that's temporal correlation. So
Sir, what
CNNs.
is like? Can you explain with an example, like what is a spatial and temporal correlation?
So for instance, let's take this image for instance, right? Like if I take two areas that are nearby in this image, right? They are highly correlated because they contain very similar information, correct? Because this is a bark of a tree, probably has very similar pixels and pixel intensities and the color compared to somewhere closer by, right? Now, in this case, this information you need to preserve in order to understand what the image is. Unless you preserve this information, if you jumble this picture up, for instance, right, then you lose this idea of spatial correlation, correct? Now, if you have a network that jumbles everything up, then that in no way can preserve this relationship, right? So that's the idea behind spatial correlation, that if you take nearby pixels and you look at what information they both contain, they'll be more or less similar. That's how an image is represented, right? There's some spatial information and relationships, and you can estimate that. Temporal correlation is nothing but, let's take a simple time series data. Let's take a sine wave, right? Okay, let's take this to be 0 then. Okay, now what's happening at some duration here is also happening here, right? So the information content in this particular place, let's say at a chunk C1, is the same as what you see or similar to in chunk C2, right? So in some sense, the information contained here is similar to here. Okay, so this is what's called temporal correlation. Right? So this will help you understand patterns in the data, right? Like if there is a specific pattern that has been seen before in the data sometime, the temporal correlation allows you to do that. Okay. So here in this case, it's spatial because you're looking at an image, which is a 2D, sort of a space. And then this could be a one-dimensional time series. Okay. All right.
Yes, sir.
So that's the idea behind spatial and temporal correlation.
So like CNNs are used only in the image data, right?
I mean, you can possibly also use it in time series data, but not for prediction, but for classification.
Like
As in you can understand that. Sorry?
convolutional means like some kind of image. Right?
Convolution can be done both in space and in time. Okay. In fact, convolution is a temporal operation. It's just that we're considering the image to be a spatial entity, and that's why we think of them more in the spatial domain. But I will talk about one-dimensional convolutions very soon, so you'll get an idea very soon in a couple of slides. But yeah, but you can do convolution on both. There's no mathematically there is nothing stopping you from doing that. Okay. All right. So let's put it in context. Let's take this image, right? Now, what's the spatial correlations here that you see? That you see a person in sort of a park standing and throwing a frisbee, right? Like you're seeing that. And there is also temporal information here in some sense that you can see features of the person in such a way that she has thrown a frisbee. So you can think about this information to be in some way encoding some of the temporal relationships between what has happened and what is currently seen in the data. Right? Now, in order to extract these relationships, we use an operation called convolution. Okay. So the idea is that you want to extract these features, features from this locally correlated data. That is, the person is extended his arm and then there is a frisbee nearby in the air. The relationship between these two is in such a way that you can interpret it as a woman throwing a frisbee, right? That's what the interpretation is. And that interpretation would be different if the frisbee was, say, somewhere here, right? If the frisbee was not here and frisbee was here and the person is looking there, that relationship doesn't make sense, right? Unless the frisbee is in a position where it relates to the person actually throwing the frisbee, that makes no sense. Correct? Or if the frisbee is at the ground here somewhere, for instance, right? Then it'll be a very different interpretation, right? Then it means that the person is, if this wasn't here, then they are basically looking at something in sort of an awe, or we are looking at some sort of a surprising thing. That's what it will look like. So this spatial relationship between the woman and the frisbee is what's giving rise to this form of, spatially and temporally correlated data, which is what we are trying to understand and get some semantic meaning out of this picture at the end of the day, right? Got that idea? So given that, this idea of convolution helps extract features from such locally correlated data. We'll look at how it does that. And importantly, what we also have in CNNs are the output of convolution, right? This mysterious operation, which we'll discuss, seems to be also passed through nonlinear activation functions, which we have looked at, right? And what that does is helps us learn certain abstractions from the image. Lets us learn those things that are important in defining what the image is about, and embeds this nonlinearity in the feature space. That is, there are certain features that you are extracting from this image, and it tells you how to interpret those features in a space that can help you separate out things that cannot be separated linearly out. Like, for instance, things like the relationship of the person in this particular position and the frisbee being in this position interpreted as a woman throwing a frisbee, for instance, right? Like, that's a very nonlinear operation. Just by combining information, you can't get that piece of semantics. And at the end of the day, the ultimate aim is to learn semantic information from images and difference between images, right? Like whether it's a cat or a dog, or in this case, if you can use networks that can also generate some text, it'll tell you that this is a woman throwing a frisbee in a park. Right?
So like
And
what
so
is this semantic information?
semantic information is what is happening in the image, right? What is the meaning of this image? So if I give you this image, what will you say about this image, right? If I show you, if I don't show you this, what would you say about the image?
It's the women's try to say, throw this.
Frisbee, right? Like she's next to a child in a park, for instance, right? Like that's what you would say. That's the meaning that you are getting, right? In fact, what your brain is seeing also is a set of pixels, right? And it's interpreting this information from this, right? So we want a network to be able to do that as well, right? And that's the whole idea behind CNNs. We'll discuss some of those relationship to actual brain, but I hope this point is clear, right? We want to extract what is the meaning of this image by looking at it, right? And we want networks to be able to do this.
So, but in order to explore the idea of
Mhm.
like forwarding the output of this convolution
Mhm.
to the nonlinear activation function. I mean, I know you
Mhm.
will be deriving it later, but for the intuition point of view.
Yeah.
So, can you explain it? Sure.
So the idea is that if so exactly, let's take the example of the feed forward networks, right? Now where we had nonlinear activation functions, why? Because we wanted to warp the space into things where into a space where things could be linearly separable, right? Things that were not separable at one level could be separated, right? And in this case, that could be information about the woman, and the frisbee could be identified, but the relationship of the woman actually throwing the frisbee is a very non-linear sort of an operation, right? That has to take into account the entire body shape of the woman, right? Sort of see that, and its relationship to the frisbee. As I told, right, the frisbee can be anywhere, and that's why and the frisbee being here makes that information much more. So the combination of those two features have to happen in a certain way in order to then give you the information, that the semantic information that the woman is throwing a frisbee. So that's what the nonlinearity does here. It helps you combine features in such a way that can at the end of the day give rise to differences between images or extract information between them. So example, I also gave you the example of a samoyed and a wolf, right? Where we saw that at the lowest levels things could be the same, but they are belong to very different classes, or at that smallest level things could be different, but they belong to the same class, right? Now at that level, if you do not take all these local features and mix them non-linearly, you won't be able to understand whether it's a samoyed or a dog or a wolf, right? Because the features that separate them are these gross level features and not the fine grained ones. Okay.
So like these non-linear functions,
Mm-hmm.
these activation functions, like how we decide which I have to select this activation.
That I'll tell you. Yeah, exactly. That I'll tell you. There is a rationale for it. Okay.
Okay.
Okay. All right, guys. Any other queries here?
Sir, one thing is I wanted to understand that the job of CNN to identify the objects
Right. Right.
or the relationship between the objects
Mm-hmm.
is a more of a, I mean, I might be wrong, but it
Mm-hmm.
more of a context-based scenario which can be a text attributed to a text problem or under describing a picture. These are
Mm-hmm.
two separate things.
They are
So
separate problems. Yeah.
agreed, but why do we want to know the relationship between the freebies, this disk and the
Mm-hmm.
woman? We just want to identify
Unless
the
you know that.
object, right?
Mm-hmm. Okay, that's one thing, right? Identifying the object is one thing, but if you don't understand the relationship, how can you make any sense of what this image is compared to, let's say, if the frisbee was not there and it was there on the ground, right? Those are two different contexts, right? in terms of if I give you those two images, would you say the same thing about those two images, or do you want a network to say the same thing? It can still figure out there's a frisbee there, there's a woman there,
Yes.
but the local correlation between the woman and the frisbee in that case, when it's on the ground, is very different from when it is here, right? So that is what you want to extract. You want to extract that meaning out, right? And that comes from these local correlated data, right?
So the relationship between the or the temporal or the spatial relationship between the freebies and the
Hmm.
lady will ultimately help us to describe the entire picture in terms of
Picture. Yes.
restructuring or recreating that picture in the final output.
Right. It could be done. It could be then done for. It could be then taken to anything, right? It can be then taken to classify the image. It can be then taken to interpret what the image means. It can be then taken to even restructure, as you say, the image into something else as well, right? But that sort of invariant representation of whatever it is. So if this entire thing shifts, and so that the lady and the frisbee are here, your interpretation of the image should not change, right? Then it's still a woman throwing a frisbee, but she's in a different location, right? So you have to be invariant to these changes in the image. That means you have to extract features that are so high level and abstract about the image that you can make
Abstract
some
means
sense out of it.
high level abstract means. Yes.
So high level is in low level is what are the micro level features, right? Like at this level compared to at this level, right? So are you seeing the image as a whole and extracting meaning, or are you seeing only parts of it and then doing it? That's sort of a crude representation of high versus low.
So I have a question in that. For example, uh, there are some features just like they have very less contribution in terms of pixel in the complete picture,
Mhm.
and we do some kind of algorithm so that the image size is reduced and we compromise some of the
Yeah.
pixels, and later they completely vanish there.
Yeah.
So because it's not in our hand that for some area we don't reduce the pixels, and for other areas we can. So
Mhm.
how we will deal this kind of problem?
Yeah, we'll look at that. In fact, there are some ideas where when you can do convolution, but you can skip certain pixels and so on. There are ideas like that. But
Obviously.
typically, reducing the pixels is in some way reducing the dimensionality, right? Now, if two things are very spatially correlated, if I drop one of them, still I retain some information too. So it's not that I'm losing some big thing about it. As long as it is done with some reasonable level of resolution, it's still going to tell me something about the image, right? So but then it makes the problem more computationally tractable. That's the idea.
Yeah, because in this picture, if you remove this three disc, so it seems like the woman is asking someone to chase the thief.
Yeah,
So
yeah,
it's
absolutely.
completely.
But that's the thing, right? If you remove that, then that changes the entire meaning of the image, right? The
Mm.
semantic meaning has changed. So this is the important stuff, right? There are certain information that even if you get rid of does not affect the outcome, but there might be certain locally correlated features. If you remove them, then that has a that completely changes what the image is. Okay.
Got it.
Yeah, does
Sir, also one question on leadership part. Like some of the member from PGD batch are waiting in the lobby. If you can allow
Sorry,
them
who
or
are
maybe
in the
add them.
lobby?
Yeah, some of the PGD members are in lobby who
Okay, why
belongs to this
aren't
batch.
they? I mean, can wait? Let me because I can't just keep switching
Yeah,
back and forth, right? Like it's very distracting.
yeah. Okay.
Admit. And what I would suggest is Ashutosh here? Huh.
Yeah.
Ashutosh, can you please send me the emails of all the people in PGD so that I can add them to the classroom so this does not happen, right? Because it's
Yeah, sure,
very
sure. I'll
distracting
just
in the
share you
morning.
the all names.
Please, yeah, do that. Yeah, thanks.
Yeah. Thanks.
I have a question.
Yeah.
Does this semantic information is there also in the fake images context, like where these days we
Yeah. Obviously, that's how they are done, right? In some sense, at the as CNNs are trained and you get to the highest levels of abstraction, you have the semantic information. and you can deconvolve that. And in fact, you can play around. If you remember our last class where we were talking about variational autoencoders, right? So imagine a CNN, right, which can be used to, which is trained on a lot of images of, say, objects, okay? And you are taking, and you're sort of using that image database and then constructing a higher level abstraction of all these images. But at the highest level, you are using an autoencoder, for instance, right? Let's say, for example, a variational autoencoder. In fact, you can use that combination in order to generate new images, which will not look like the objects that you have already used or already trained in the network. So you can generate new images by using such combinations. So in fact, CNNs can be used to construct embeddings as well of images, right? Like some form of compact representations of the images that can be used to then generate new data, used for classification, even taken to certain NLP models to actually predict what is the information content in an image. And there are many things that's possible. But that's why I call this the architectural backbone of modern AI, right? Like, there is a reason why this is very popular and very useful and has found its way in a lot of these companies, which have now are using pretty much many forms of CNNs in your phones and devices. Yes. Okay. All right, guys, let's move on. We'll take more questions as it comes, but let's just talk a little bit about the history, right? Very quickly, because around about the 1990s is where we saw CNNs come into light, right? Actually, in fact, LeCun was the first person to actually talk about CNNs, because they applied it to some topological data, and or be it images and time series, and showed some performance boost. Till that time, people were struggling to get artificial neural networks to work on image-like data, and the inspiration actually came at the right time, because at that time there were two neuroscientists, Hubel and Wiesel, if you have heard. They got the Nobel Prize for their work in the primate visual system, where they showed that the visual hierarchy has this sort of property where you have the CNNs started resembling the different areas of the brain that is involved in the visual processing. We'll discuss a little bit about that in the coming slides. But the idea of receptive fields, you must have heard this word, right? The fact that how processing of vision happens in the brain has a lot of similarities, and the work of CNN was inspired from this, the brain-like architecture of visual processing, and how that can allow you to extract low, mid, and high level features, right? Now, we discussed that in the first class, when low level features could be as simple as the lines, right? Edges, the orientations, and so on and so forth. The mid-level features might be some a combination of these low-level features, like the combination of these lines to form the outline of the body or the face, and then other things. And then the high-level features might be the entire construct as a whole. That is, in this case, the woman, and the frisbee together in some context. Right? So these forms of features can be extracted from CNN, and that's one of the ultimate, strengths of convolutional neural networks, and we look at how it's able to do that. Okay. Now, let's talk about the canonical CNN architecture. And when I say canonical, I mean that this is basically the primitive form of CNN architecture. There have been many adaptations recently, right, which can combine such an architecture in many ways to give the ability of the model to do different things, be it from image classification and image context representation and everything. Right? And you must have seen this picture before, but before that, we have to discuss about three things in a canonical CNN architecture. There's type of layer and what function and purpose it serves. So first is the convolution layer. As the name says, convolution neural networks perform the operation of convolution, right? But what is the purpose of it? The idea is to create filters or kernels. We'll discuss about them, but the keyword is filters and kernels, okay? And it is used to create what are called feature maps, and we'll discuss what are feature maps. But I'm just introducing these ideas to you so that these words make more sense as we go deep into it. Okay. Then there is what's called a pooling layer. Okay. Often we want information to reduce in dimensionality because images could be pretty large, and we want to understand what is the abstract aspect of the image, what does it represent at the most highest level, and in fact reducing the dimensionality in a very systematic way helps you do that. So the idea of dimensionality and increase receptive field size, so this we will talk about. Those are the properties of what's a pooling layer. Okay, so by the name, you're sort of pooling information together in a way that can help abstract the image or reduce its dimensionality. And finally is what's called the fully connected layer. This we have looked at. It's pretty much, we know that the fully connected net layers are very good at prediction or classification, and they're pretty much similar to feed-forward networks. So in some way, this architecture is a combination of a convolutional pooling layer and a fully connected layer, and they are organized in such a way that then they can basically form representations of images, spatially correlated data like images, or in fact even sometimes videos. CNNs plus RNNs have been used to actually do video classification, video-based segmentation, and there are many applications of that. But these are the basic three layers, okay? And if I look at the typical CNN architecture, this is the picture you would have seen everywhere. I'm just taking it from the internet, but there are many variations of this, but this is the basic one, okay? So you have an input, which is likely an image, let's say, and you have what are called kernels, okay? Kernels, we'll establish what kernels are exactly. You can think of them right now as some way in which you can extract features from this image, right? And perform this operation called convolution. Okay? And we'll talk about what convolution is, along with passing it through an activation function. In this case, the activation function people typically use for CNNs is what's called a rectified linear unit. Rectified linear unit. Okay, so unlike other sorts of activation functions, as we have seen, a ReLU, if this is your x, this is your f of x. Anybody have an idea of how a ReLU works?
Straight line for y equal to x till 0, and then less than 0 it will be 0.
So that means f of x is
Y equal to
x
for x
at
greater than 0.
greater than 0, and then
0 for x less than 0.
not equal to 0, right? So you see something like that, right? Now, is this a nonlinear function?
Yes, overall
Yes.
nonlinear.
Yeah, it is a nonlinear function, right?
For x greater than 0, it is not.
It's not, but on a whole, this is a nonlinear function, right? So it still has some nonlinearity in the sense that any input that is less than 0, it sets it to 0, right? So, and then any input that's greater than 0, it scales them proportional to the input. And so this is another way of embedding nonlinearity into the model, right? We'll talk about why ReLU is used compared to other types of activation functions that we looked at before. But that's what is happening at each of the layers, like there's convolution plus passing it through a nonlinear activation function, followed by a operation called pooling, where we are trying to reduce the dimensionality. So If the image is of this size, now the image is smaller. Okay, and then there is another set of convolution and nonlinear operation, and then there is further pooling, and then the image size reduces again, and then so on and so forth. Okay, till a point where things are all flattened out, right? You go to a level of abstraction that you think is good enough for this type of input space, input object space. And then you flatten it out, and then comes your fully connected layer, which is exactly similar as that of your deep feed forward networks. And finally, at the output, you have classes which predict the probability of an image class, right? So you have your classes, and then it predicts the probability. Typically, we use a softmax activation function. We'll look at each of these components individually so that you are able to understand everything and then piece them together as a whole. All right. Okay. So the idea is that this is the architecture. You have convolution, you have pooling, you have fully connected. That's basically the entire CNN. But this particular combination, the convolution and pooling, can repeat many, many times, right? So in this case, this is repeating once, twice, 3 times, right? So this has now 3 layers. This can be n layers, like depending upon the type of problem that you have, depending upon the size of inputs that you have, and so on and so forth. Okay, so this can repeat n times. Okay, and at least by intuition, what do you think increasing depth gives you? That means if you increase this number of layers,
More number features?
more number of features, or
Yes, number of
Complex features.
more complex features or more abstract features, right? That's what is, I think, the more right word. In this case, wider, as in instead of looking at very local information, right? At every step, you are slightly looking at a bigger piece of information, right? As the dimensionality reduces, and you start developing more abstract features. Yeah. Okay. And at this level, things could be better explained. For instance, things could be better separable. Spatial information is still preserved in some sense, right? And so, distinguishing between the Samoyed and the dog, the Samoyed and the wolf problem would become much more simpler to solve in such an architecture compared to if you use just a architecture like this where everything mixes, right? So you can see that spatial information is still preserved, but how is it preserved? What sort of features do you extract? Those are a question of what CNN is all about, so which is what we look at. Any questions here?
Sir, if we increase number of in, so it will lead to the underfitting.
Will it lead to underfitting? That's a really good question. Yes, possibilities are there. You are right. But can you? Okay, why did you think that? Do you have an intuition? I'll tell you the answer, but I just want to hear.
What I'm thinking, sir, like if you increase the number of in, then the number of feature will get reduced, right? So at point of time, you'll end up with some losing some important features.
I see. That's your no. So my reasoning is slightly different.
So maybe if you're creating more abstract features, maybe the correlation in spatial terms is lost, I guess.
No, right? At the end of the day, that's why you are looking at very high level features or wider features, right? So at the end of the day, you just don't want just this local information. You want to look at bigger and bigger part, so that at the end of the day you understand that this is a zebra. But if you look at just this part, you might even mistake it for like a white tiger, right? White striped tiger, for instance. Right?
So,
So
like,
taking into account more and more bigger and wider features, and that makes it much more abstract in some sense, that you are able to get what is the zebra-ness about this image, right? Or what is the tiger-ness about an image which is of a striped tiger, for example. Okay, that's the idea. But the reason why, if it with very large n it might be a problem, is because of training, right? This is a network which is also again trained using backpropagation, right? The error that you get at this point delta is backpropagated. With many n, you have issues of what's called the vanishing gradient. We discussed this, right? Vanishing gradient problem. And in fact, this brings me to a nice segue of why we use ReLU, and I think I gave you the answer. Why not any other activation function like say a tanh or say a sigmoid? Why is ReLU used? Anybody have any idea or any thoughts?
Sir, I think as long as the number is greater than 0, it will give some positive output as compared to
Right.
where
So
it
this
might.
is a sigmoid. I mean, these both are sigmoid. This is a tanh. This is a ReLU. Okay. So why
This
not?
may have to do with the color codings
Mhm.
of the picture.
No, these are the activation functions, right? So
They handle the gradients much better.
yeah, that's actually the answer, right? Imagine, right? Like if you can see, when I pass this information, the gradient at this level is virtually 0, right? Yeah, there's no gradient compared to here. Whereas if you look at this gradient is going to be the same at all levels of this function, because y scales with x in a linear fashion, right? And in fact, the gradient is what in this case?
1.
1. Very good. Right? So the problem is that at very extremas, the sigmoid function can give rise to these vanishing gradient problems, right? Sigmoid or tanh be it. And we typically don't want that. And another thing is that there's another advantage of using ReLU. Anybody can guess?
It is faster in computation.
Very good, very good. Yeah, it's much faster in computation. You can compute. So yeah, as everyone said, the gradient is very simple to calculate. These has exponentials in it, right? This is 1 by 1 plus e power minus lambda x, and this is tanh is 1 minus e power minus x by 1. Yeah, I mean, correct me if I'm wrong. There's plus or minus below. I forgot. Anyways, it's these are exponential functions which are harder to compute the differential for and all that. But I mean, we do have an analytical form, but this is very simple, right? Like this is and also another idea is that this is in some sense scalable to what a real neuron would be as well. Like with graded inputs, it typically is graded, but neuron also becomes nonlinear at some point of time. So this pretty much captures the linear aspect of the sigmoid, but maintains the non-linearity by strictly setting out things to be 0. There is one more advantage of using ReLU, but this a little bit of a subtle point. If anybody can make a guess or a guesstimate or an educated guess, it'll be good. Just want to know. There's one more advantage of this.
The features will be retained, I think.
There is something to do with features, but what?
Negative is 0.
Sorry?
Negative is 0 here.
Yeah. So what is the result of that?
So we only get one option at the end, like one output.
Very,
Like,
very nice. So that's what is that called? So if most of things in a data set is 0, right? Let's say.
Sir, sparse.
Sparsity. Very good. Very good. Sparsity.
okay.
Very nice. Good. So you guys are on board. So sparsity helps you classify certain things which has contrast in them really well, which pictures or most of them have, right? Pictures have contrast because they separate image from the background, right? And we are trying to often look at that aspect very importantly, because that tells you a lot about what the image is, right? If everything is blurred with the background, then it's very hard to understand that, correct? So sparsity helps you extract this contrast information, right? And that's why one of the reasons why people use the ReLU function.
Sir, I just want to ask: is the pooling is completely explained, or you will?
I will explain it. No, I haven't explained anything yet. This is just, we are talking very high level. We'll look
Yeah,
at convolution, pooling, and everything one by one.
Because my problem is okay. Sorry. Okay.
So we'll look at it. We aren't gonna just stop here. This is just a high level discussion. Okay.
Yes, sir. It is easy to do the calculation as well.
Yeah, it's pretty simple. Okay, so in fact, to do the math for a CNN, you typically even don't need college level math, right? You just need some high school level math to do this. But it happens so that, you know, putting things in this sort of order helps you do very nice, you know.
बाकी sigmoid वगैरह में calculation heavy हो जाएंगे.
Exactly, yeah. And sigmoid is typically a little bit more computationally expensive. And I told you, right, there are many advantages of using ReLU. Vanishing gradient is one of the biggest advantages. It prevents those problems. Right? But there are also computational efficiency and sparsity. Sparsity is one of the interesting consequences of having a ReLU activation function. That means that at each level, when you compute the features through convolution, you can push them out through this activation functions that can highlight certain features very well, right, at the end of the day, which might be important in classifying what the image is about. Okay. All right, so let's move on. So we'll finally talk a little bit about the inspiration from CNNs, because I think I heard a question even from last class, right? How do people come up with this? And as I say, the idea comes from thinking about interdisciplinary things, right? Like brain is one of them that has inspired a lot of such architectures, although there are certain streams that have evolved independently too. But for CNNs, definitely the human visual system. So this paper, so every paper has a link below, okay? So you can just go and put that in Google and you'll get the paper. So if you want to learn more about it, you can do that, okay? So what they saw was that in the brain, to give you a very brief neuroscience idea, is that brain also has a way to take sensory information via our eyes. Our retina are like, you know, camera detectors, if I can make that very crude analogy, right? And those information go via several stages to the back of the brain, where it's what's called the visual cortex, okay? And there are many stages of the visual cortex. There is V1, V2, these are levels, okay? And what people have seen repeatedly is that there is a very nice correspondence between how the brain organizes vision and how that inspired the organization of deep neural networks like CNN. Okay? First of them was this idea of what's called receptive fields. Okay, so at the level of the retina, even, so if you can look at this, each retina, this is our certain types of cells in the retina called simple cells, right? They look at a small space in your input visual space. So in some sense, they take information about these very local features, all right? And a bunch of simple cells then combine into what are called complex cells, right? where if each individual cell has a receptive field which is small, this complex cell now looks at a wider, erase that, looks at a wider reach, right? And a bunch of complex cells might then pool to give you another type of cell which probably looks at a bigger space. Okay. And that is the effect that you are pretty much getting in a CNN. Right? Now, the lowest levels look at very local features of the image, right? Because they look at kernels, and the minute there is a reduction in the dimensionality, now the next layer can look at a bigger part of the image, right? And then you move on, and then that's the further reduction in size, and the next layer looks at a much bigger part. And in some way, you are now looking at wider and wider features and extracting at each level things that are very relevant for making the objective of the problem. And the objective of the problem is to either classify the image or do something with it. Right? Let's take image classification. That's what the objective is. We want to reduce the error between what the image was and what the network is predicting. Right? And that is the way in which the kernels are then getting updated in order to do that. But can you see the analogy with the brain? That is, you see these small receptive fields which grow bigger and bigger, right? And that's the same thing that's happening at the level of the CNN.
Sir, one question here, sir.
Yeah.
So when you mentioned complex cells to simple cells, yes, it will be broken down, and later which we will be getting a bunch of all the simple cells, which will be collectively giving us a bigger picture or bigger cell.
Yeah.
So in this context, sir, is it not just related to image, right? Like it is also related to like all the subjective items that we analyze. For example,
that's true. That's true. Yeah.
So like the simple cells from different subjects that we analyze. At the end of the day, when we think about it, like probably we will get the bigger picture of different things as well. So even in CNN, like is it the same way?
Yeah, as in at the end of the day, what you want to do with it is different, right? Like for example, in this architecture, you can build representations till this point of different things, right?
Yes.
Now, what you do with this? Do you want to classify? Then you use a fully connected level. Do you want to make new images out of this? Then you put an autoencoder here and do that, right? Now, you can imagine in the brain also things are pretty much happening like this, right? Like you make compact or abstract representations here, right? And you decide what to do with this later, right? But you build these representations, and the convolution plus the nonlinear activations along with pooling provides the architectural backbone to do this abstraction. Right?
True.
Later, what you do with this is going to be the objective of the problem. Do you want to classify, or do you want to just recreate the output? That is, you come till this level and then you do a deconvolution. That is, you just take everything back again to the main image, right?
Right, sir. Right.
And so you can do many things. Yes.
Got it. Thanks.
Yeah. And in sense, you should start thinking about CNNs as a way to develop embeddings of images, right? So this final layer is some sort of an embedding, right? So you are taking this entire image and then embedding it into this feature vector here at the end of the day, which is a very compact representation of what this image is about, right? Then you use this for any purpose that you want, to classify, to create new images, to reconstruct the same image, so on and so forth.
Okay. So sir, this n is actually a hyperparameter, right? I mean,
yes, this is hyperparameter. This you need to play with. Play with this.
And do we have control over, what features it is looking at each layer, or what features?
We do. In fact, the operation of convolution, which we will discuss, is going to slide over this image at every time point, sorry, at every spatial point, and we're gonna get the next thing. So we do have control over how the movement of the kernel happens over the image. Okay, so we do that. Okay. So we look at each of them. So don't worry about it. We'll discuss everything very detailed. So these are just to set the next lectures up. Okay. So another very cool thing that I'll show you, which has a very nice analogy to the brain. So there are parts of the brain in what are called the inferotemporal areas. No need to worry about the name, but there are areas in the brain. Temporal is near your temples or your side forehead. There are areas in the brain, right, where if you record from them, they tell you about object detection, right? That is whether that object was a particular image of a face, image of a object, or object, face, and many things, right? Detection. So what they've seen is, if you take an image or an image data set and train it via a convolutional neural network, at some level of a hierarchy, the activations of the one of the deeper layers resembles the activity of those cells which have these very similar properties of object detection in the brain. Okay, and that was there was, and I'm going to show you another paper which established this very interestingly. But these were these early underpinnings people were thinking about. Although, see, if this paper is back in 2021, so it's very recent, right? Although the inspiration came from this, people then started seeing this analogy even further, right? Like, if you go to areas of the brain that are specialized in detecting objects, and if I train a CNN and look at the deepest layers, or at least to some level of depth, do they act similar as if it is the same areas of the brain? So in fact, you can imagine if that the representations were formed in the early visual areas, and more if you go to higher visual areas where there is object detection, that is like this fully connected network probably there, right? Very likely that there is a classifier there sitting and trying to understand what these different representations mean. And if you look at the activity that's just prior to these levels, then you can correlate them with the activity of what is seen in the brain, right? So this is a very interesting way to make the bridge between the human visual system and an artificial visual system, right? So you can call this as an artificial visual system in some sense, because it's able to generate representations with which you can understand images. Okay, so this was another idea. And in fact, there was another paper, which is a very interesting paper. I would like you guys to go read this if you are interested. Is like, you can see even brain-like functional specialization in CNNs. Okay, so this was a paper by a very famous MIT neuroscientist, Nancy Kanwisher's lab. You have heard of her name. So she even talked in one of the conferences that happened in IIT Jodhpur last year, in 2023 January. So what they showed was, if you take a CNN, okay, there are many different types of architectures. Forget about the name. There is a specific type of architecture called VGG, visual geometry based images based architecture. So it doesn't matter what the name is, but there is a specific type of architecture that seems to resemble what the brain does very closely, right? So it has around about 15, I guess 1, 2, 3, 4, 5, around about 13 convolution layers, and then finally 3 fully connected layers, right? And what they did was they trained the CNN on 3 things. They trained the CNN on faces, they trained the CNN on objects, and they trained the CNN on both. The hypothesis or the question was, does brain have areas that are specialized in understanding specific types of objects? For example, are there areas in the brain that are very specialized in looking at faces or classifying faces, okay, and classifying objects? In fact, there was a hypothesis going on that there is a region like that, and they used CNNs to actually test this idea. Okay, and what they did was they first trained the CNN on only faces. Okay, so it was doing really well on faces and not so well on objects. And then they trained the CNN on objects, which did well on objects and not on faces. Okay, so if you do that, but very interestingly, if you train a network which is trained on both, okay, that is faces and objects, what they saw was the things that was only trained on faces and the thing that was trained on both were very similar in accuracy. Okay, and then the thing that was trained on objects only and then the CNN which was trained on both also had very similar accuracy. So what can anybody think about what that would mean about the network? What does that say? Any guesses?
Like there's no specialization.
No. So in sense, okay, that could be good. So the point is that if I train a particular CNN on objects, right, and I give faces to it, if objects were enough to get me the backbone of what it is to identify a face, then if I trained a CNN on objects, it should also do well on faces, right? But it does not, and vice versa. That means there are very specific things about faces that we are able to extract, or we are able to do that in order to be able to recognize them. But if a CNN is trained on both of them, let's say for example, then it seems like the dual CNN performs the same way as a single CNN. Okay. So why would that happen?
Maybe because of facial features.
Because of feature extraction.
Could be because of facial features, because object can be classified, but the facial features have more data points than an object of.
I mean, I think they made sure that they balance this out. Like there are equal number of data images that they gave for both objects and faces. So I don't think that's a problem.
So because the principle still remains the same, building from small level details to higher level.
Yes. Right.
So
I mean, the expectation would be that if you train it on both, there should be some deficit in each of them, right? Like maybe, but it turns out so, at least what they observed from this paper was the network itself functionally specialized itself so that it can do well in both faces and in objects. And in fact, what they did was very interestingly, they did like a lesion study. That means they took some layer of this CNN and they ablated those neurons that are very specific for faces, okay, that had face representations. And what they saw was only the face representation came down for the dual thing, not the object one. And if they did the specific thing for object, only the object thing came down, but not the face. So that means even in such an artificial neural network, without imposing any constraint, just by training with objects and faces, you have obtained a network that is specialized in doing face and object recognition separately in some sense, right? That is, one is not interfering with the other. And this was a very nice way of saying that such an architecture can itself lead to functional specialization, right? Without imposing any sort of new constraint. It is just this architecture. All right. So this is a very interesting paper. I would urge people to see and read this, because it gives you a very nice perspective of what's happening in the brain as well as in a deep neural network architecture. But my point was, such networks have been used to even explain how the brain works, right? So that's a very interesting link.
So could we have achieved this by taking the embeddings that are generated out of the individual ones, thought of merging them together and creating.
Oh, that's a
one-
very nice idea. I think they've done all this exercise in the paper too. That is, take the embeddings at this level, right, between both, and then do it. But that means that you have already trained them at separate levels, obviously, right? Like you are making this functional segregation here. But if you do not make that functional segregation and train a single CNN on both, still a functional segregation arises, right? That was the point of the paper, right? So that means that a same network, just by changing how you give the input or the input statistics, has the capability of forming functionally specialized networks. Okay, and that is the power of AI models right now, right? Because the level at which they abstract information can also give rise to functional separation, right? And this way you can look at interactions between objects and humans, as well as look at them separately, right? So there are very interesting ways in which you can interpret this result, but just to give you a small flavor of that. Okay.
So can this be extended to like multiple types, like, or is it just limited to only two
Okay, so
types?
they were
like,
interested. So their lab does a lot of face work, face processing. So if you know that there is a brain area called the fusiform face area. Okay, so this lab studies this fusiform face area very extensively. So their motivation was to establish a fact that there is an area that is very specific for face processing in the brain, right? And then they use CNN to show that that might arise with such an architecture. You don't need any specialized, architectures or a separate sort of a specialization for faces. It just so happens that if you give faces and objects together, it will just segregate in this network. So that was the point. Okay, but you can try this out with other things as well, right? Because there's something very special about faces, if you imagine, right? Like the eyes and the nose in between, the ratios between them, and then picking up these high level features about the face. There is something that is unique about faces, and we are really good at recognizing faces, right? And yeah. Okay, so I think we are out of time for today, but I hope that was a initial intro that gave you a taste of what we are about to see, because next we will look at convolution operations and go into the sort of nitty-gritty details of it, but hopefully that helped you understand what CNNs is about.
Totally, sir.
Okay, cool. All right, guys, I'll see you then. If there are any more questions, then let me know. Otherwise, if people have to go leave, please do.
Right. Thank you so much, sir. Have a great day.
Thank you. Yeah, we'll see you tomorrow, 9:45.
Thank you, sir.
Thank you, guys.
Yes, sir. Sir, I will meanwhile drop you the list of.
Yes, please do. Yeah, because then this can be.
Sure.
This doesn't have to be a problem, and they don't have to wait